We're going to take a look at linear combinations. So it's exactly as it sounds. It's a combination of linear equations. Now there's a few other things that we're going to talk about, and they're introduced to us in our terminology. First off, a linear combination is an expression in which all variables are raised to the first degree or first power, and none of the variables are multiplied or divided to each other. Here's a simple example of a linear combination. We have 2x plus 3y is equal to 24. So we are doubling our first variable, we're tripling our second variable, we're combining them to equal 24. Now, the standard form of the equation of a line, this is different than the slope-intercept form of the equation of a line, which we learned in our previous notes. Our standard form goes like this: ax plus by is equal to c, where a and b are both non-zero numbers. So another example is exactly the same one that we just had. We have 2x, oops, this is supposed to be an x, 2x plus 3y is equal to 24. A couple other terms that we're going to talk about today are continuous functions and discrete functions. Now remember, continuous graphs have the domain of all real numbers. If we were to take this graph here, this solid line, and compress it on the x-axis, or our domain, it would be all real numbers. Whereas over here on the right-hand side, this is an example of a discrete graph. Discrete have only domains that contain specific values, such as integers or some counting numbers. So here, if we were to compress this on the x-axis, we would see that there'd be gaps in our domain. They would not include values such as 0 or -1 or possibly 4, but they would be described as kind of like these broken pieces or parts of a graph. And that's an example of a discrete function or a discrete graph. All right, into today's examples. In professional hockey, a win is worth 2 points, a tie is worth 1 point, and zeros are worth, just kidding, losses are worth 0 points, which makes sense. Early in the season, our team has 11 total points. We want to write an equation that represents the relationship between the team wins, losses, and ties. So we're going to let W equal wins, L equal losses, and T equal ties. So an equation for this might look something like this: 2 points for every win, plus 1 point for every tie, plus 0 points for every loss is going to be equal to the total number of points. Now, in our team's case, we know that we have 2 wins plus 1 point for each tie. Now, because it's 0 on our losses here, we're just going to ignore that because 0 times anything is just 0. We know our team has a total of 11 points. And this is an example of a linear combination where we have W and T both raised to the first degree or first power. We're combining our wins and our losses to equal some total. So here we want to make a table of all the possible wins and ties this team could have. So if they have to add up to equal 11, we could start off by having 0 wins and 11 ties. Our team could have 1 win and 9 ties, 2 wins and 7 ties, 3 and 5, 4 and 3, or 5 and 1. And that's really where it has to end. Our team cannot have 6 wins because 6 times 2 would give me 12 points, and we know our team doesn't have that many. So here are all the linear combinations. Now, if we're going to go over here on our graph and give a little visual representation here of what we're looking at, we'll plot all of these points: 0 over and 11 up. And notice that my W is plotted along my x-axis and my ties are along my y-axis. 1 over and 9. And we're just going to continue down in this fashion here. You can see our slope is this -2. For every win, I'm going to take away 2 losses, so on and so forth. Now, my question for you is, should this be a discrete or a continuous function? And it doesn't make sense for it to be continuous because you can't have a partial win. You can only have whole number wins. So we say that this is going to be a discrete graph or discrete function because of our domain is only going to be these counting numbers, and it's not going to be all real numbers. All right, moving on to example 2. We're getting a little hungry here. We're going to go to Harry's hamburger joint, where burgers cost $2.50 and hot dogs cost $2. We're going to go out to dinner with our family, and we have a total of $30 to spend on our meal. So let's write an equation relating the number of burgers, B, and hot dogs, D, that you can purchase with $30. Well, if each burger costs $2.50, we're going to say $2.50 times B plus $2 times D should be equal to the total amount of money that we have to spend. In this case, no more than $30. So again, this is a linear combination, a combination of the burgers and the dogs. Our variables B and D are not being added, are not being multiplied or divided to each other. They are being added or combined, and they both have a degree of 1. Let's solve this equation in part A now for the variable D. If you remember doing this from a few chapters ago, that means we are going to move everything else over to the other side of the equal sign and get D by itself. So we'll start off by moving our 2.5B over by subtraction. And now we're going to divide both sides by 2. All right, when we do that, we get our equation D, the number of dogs we can purchase, is equal to we got to take 30 and divide by 2, which is going to give me 15 here. Erase that. 15 minus 1.25B burgers. All right, so we have to divide both that 30 and that negative 2.5 by 2. So here is our equation now written in terms of D, number of hot dogs. So next up, we want to give all the possible combinations of burgers and dogs you can purchase. So I'm going to make my table this time. I'm going to make it horizontal rather than vertical. Either way is acceptable. So we'll just do burgers here and dogs. All right, let's get going here on this. We can possibly buy 0 burgers. If we buy 0 burgers, we'll have $30 to spend on hot dogs, which would be 15 dogs. Next up, I could buy 1 burger. If I do that, it's going to cost me $2.50. And I no longer can buy 15 dogs, and I can't buy 14. I have to round all the way down to 13, because keep in mind, you can't buy a half a hot dog. Next up, I could go 2 burgers, which would be a total of $5 on burgers. That would leave me a remaining $25 for dogs, which would give me 12 dogs that I could purchase. 3, and now I'm going to go down to, 3, I can purchase 11 dogs. At 4, I can purchase 10 dogs. So on and so forth. I want you to continue that pattern and see all the different combinations of burgers and dogs you can purchase for $30. Let's move into our next example. Here we have a little bit of a chemistry example here. Chemists are always mixing their solutions, and they need to be exact in how they mix them. Suppose we have a particular mix that has X liters, and each of those liters has 1.5 moles per liter of acid. We have a different mix that has a little bit higher content of acid. It has 6.5 moles per liter of acid. We want our final mixture to contain 15 moles of acid. So let's start off by writing an equation that relates X, Y, and the total number of moles of acid. So we have 1.5 times X, because that's how many moles per liter are in that X solution. We're going to combine that with 6.5 Y, because that's how many moles of acid is in that solution, and it must equal a total of 15 moles of acid. All right, so here's our linear combination of solution X and solution Y, both with different concentrations of acid in them, but we're going to combine them to equal a total concentration of 15 moles. All right, it says now how many of the 6.5 moles per liter solution must be added to 5 liters of the 1.5. So this 5 here is going to be input into our equation for X in order to get that 15 moles of acid in the final mixture. It says round to the nearest hundredth of a liter. So let's solve this equation by substituting in 5 for X and solving for Y. All right, 1.5 times that 5 gives me 7.5. We're next going to subtract over that 7.5, and that's going to leave me with 6.5y is equal to 9.5. Finally, we're going to divide by 6.5. Oops, that's a 6.5. And that's going to give me the value for y. Let me check my math here. Rounding to the nearest hundredth is 1.46 liters. So we will need 1.46 liters of that 6.5 moles per liter solution in order to bring our total or our combined solution up to 15 moles of acid. All right, one more example. These linear combination problems can be a little bit tricky, but hopefully you're starting to see the pattern here. Mixtures of A and B contain weed killer and water. Mixture A has 5% weed killer, mixture B has 15% weed killer. Let's write an equation relating A, B, and T, the total amount of weed killer, as we combine the two. All right, now because we're dealing with percentages, we have to be a little bit careful here. I have to write those as decimals. So 5% is 0.05 A plus 15%, which is 0.15 B, have to be combined to give me T, my total mixture of weed killer. Next, it says how many ounces of the 5% solution must be added to 50 ounces of the 15% solution in order to get 12 ounces of the weed killer in the final solution. So now we're going to solve for A when we know that the amount of B, our 15% solution, is 50 ounces. All right. So 0.15 times that 50, again, I'm just going to check my notes here, gives me 7.5. So this is 0.05A plus 0.75 is equal to 12. Subtract that 7.5 over, so we have 0.05A is equal to, what is that, 4.5? And then we're going to divide by 0.05. It comes out to equal 90 ounces of our mixture that has the 5% weed killer in it.